Okay, pre-calc time. We are going to model real-world data with polynomial functions. You have done this many, many times. With linear functions, you did it in Algebra 1 and Algebra 2, and I think we did it earlier this year. Now, we are going to move on from linear. So this would be linear, quadratic would make a parabola, cubic, and quartic. And basically the way you decide which one you need is how many times it changes direction. If it doesn't change directions at all, it's only got one directional piece, it's linear. If it changes direction once or has two directional pieces, it's quadratic or second degree. If it changes direction twice or has three directional pieces, it's cubic, and 4, it's quartic. 5 would be quintic. We're not going to do any quintics right now, but theoretically you could do a quintic. That would be 5th degree. Determine the type of polynomial function that could be used to represent the data in each scatter plot. So not all data is linear, and to decide which one you want to use, you actually need to look at the graph of the data. In this one, if we sketched a line that followed the general trend of the data, it would go up and then down and then up again. So that looks most like a cubic function, 3 directional pieces. This one seems to change direction only once, so that looks like a good quadratic function. What we're going to do is put it in the graphing calculator, have the calculator calculate the, put it in the calculator, graph it, decide which one you want, then have the calculator give you the best fit function, check it, and write it down. So, use a graphing calculator to write a polynomial function model a set of data. First thing, we are going to want to get this r squared. So you need to go into the catalog, which is, the catalog is right above the 0. So second 0, and then scroll down until you reach diagnostic on, and just hit enter twice. So second, what are we doing? There we go, second 0. Scroll down until you get to the D's. You can actually take a shortcut by hitting the this button because it's got a D in front of it, or on top of it. Diagnostic on, hit enter again, it says done, that's all you gotta do. To enter the data, I hope you all remember this, stat, edit, you put your X data in list 1 and your Y data in list 2. I've already entered this one. To graph the data, you have to turn your stat plot on. So second Y equals. Turn your plot on by selecting it and making sure that the on is highlighted. You can choose the type of graph. By default it should be a scatter plot, that's what we want. By default it uses list 1 and list 2, that's also what we want. We could change it if we wanted to, and you can adjust the other stuff if you want. We're going to plot this. It's statistical data. If we just plot a normal window, well, we get this, and that's not awful. We can kind of see the curve, but there's a much better way to see the data, and that's by using zoom 9. And that will zoom us right in on our statistical data. Okay, up, down, up. So that looks like a cubic function to me. So I'm going to want a cubic regression. For that, I'm going to go to second, not second, I don't know what that was about, stat. And then I'm going to go to the right to get to the calc menu, and I'm going to choose cubic regression. Cubic reg. So stat, calc, cubic reg is number 6. For this, I know I've harped on linear equations about storing them, and you can do this vars, y vars 1, 1, and that will store the result in y1, but for these I actually don't want to. Because it's important that we check this and see that we haven't rounded off something important, so it's better if you don't do that. So all you got to do is go down to calculate. If you have, if you didn't get this when you did cubic reg, that's fine. It doesn't matter. What you got is what we're going to get on the next screen. So when you do cubic reg, you should either get this screen or this screen, and we want to go here anyway, so it doesn't matter which one you got. So these are our coefficients. This one makes the rounding really easy. To tell how many places to round to, it really depends on the particular function. So that's why I say you've got to graph it to see. In this one, honestly, we can round to the integers. So this will be, it's the same as these numbers. So 1x cubed minus 3x squared plus 1x minus 5. We need to check that that's right. So we go into y equals, plug in the equation we just came up with, x to the third minus 3x squared plus x minus 5. If it's not right, then either we did something wrong or we need to go back and maybe not round so many dozen places off, but actually include more of the data. But this is a beautiful fit. I think that's a very good fit to that equation, or to that set of data. Also, the r squared, the r squared, the closer r squared is to 1, the better your fit. This is an extremely good fit. So this is the function which models our data. On the back, example 1, that's roughly linear. This goes up, down, so that's cubic. This goes up, down, so quartic. And this one, you're going to put it into your list 1, list 2, and then we're going to do the same thing we did on the front. For number 4, I have now plugged my values into the calculator. I need to make sure I don't have, I've got to clear out my last y equals, or it'll just look, I mean, you could leave it in there, it wouldn't matter. Excuse me. Except that it would make your graph look funny, but, oh, I forgot. I've got new statistical data, so let's do zoom 9, so it zooms in on my new data. That looks cubic. 1, 2, 3. So stat, calc, cubic reg, enter. Okay. R squared is basically 1, so this is a really good fit. Once again, it looks like I can do a lot of rounding here. So I'm going to say 2x to the third minus 3x squared minus 1x plus 4. And I'm going to plug that in to make sure that I haven't rounded off anything crucial, because in some of these it's possible to go along thinking you're doing just fine and you've rounded off something very important and it doesn't work. Let's see. Oh, that seems to work very prettily. So that's that. That is the function which best fits that data. And why is it good to fit data? It helps you make predictions about missing values. Next one, we're going to put it in the calculator. Now, just as a reminder, when you go in and you need to replace stuff, you can type over it, but if you want to clear out the entire list, arrow up until the head of the list is highlighted, hit clear and enter. Do not hit delete. If you hit delete when you're up here, it deletes the list itself, and I don't know how to get it back short of clearing the memory. Clearing the memory is fine, but not ideal. So just be aware of that. Clear, enter is fine. Delete causes you trouble. I've entered my data. I go clear out my last function, zoom 9. All right, this seems to go down and up a little and down a little and then up. So that looks like a good 4th degree function. So I'm going to use a quartic regression. Stat, calc, 7 for quart. Enter. It's going to take longer. The higher the degree it needs to estimate, the longer it'll take to think about it. R squared is essentially 1. Again, a very good fit. I'm going to try rounding to... let's try rounding to the nearest integer. Let's see if it works. I don't actually think it will, but I don't know for sure. So if we rounded to the nearest integer, it would be 2x to the fourth minus 3x to the third minus 6x squared plus basically 0x plus 5. So let's see if that works. It might. It's hard to tell. So 2x to the fourth minus 3x to the third minus 6x squared plus 5. Oh, no, that doesn't work at all. So this is an example of one where we tried rounding it, and it turned out we lose some important data by rounding it. So let's go back and find our data again. Unfortunately, for some reason it clears it off the screen. Okay, so I think I'm going to be safer going to 2 decimal places here. So to the nearest hundredth. This will be y equals 1.98 x to the fourth plus 2.95 x to the third minus 5.91 x squared plus 0.22 x plus 4.89. So 1.98 x to the fourth plus 2.95 x to the third minus 5.91 x squared plus 0.22 x plus 4.89. Graph it. Much, much better. So always check. Sometimes you don't need to round, you don't need to have that many decimal places, sometimes you do. So always check how your graph looks. That's a very nice graph, so that's a very nice fit. Number 6, I've put in the data in my calculator, and then I went and I graphed it, and to be honest, that looks a little funny. That doesn't look like it's in line with the rest of the data. So be aware of that, because your intuition may give you some help. In this case, I made a typo. So this should have been, I made 2 typos, wow. 1911, -1, -7, -8, -5, +4, 11 again, apparently I have trouble with 11s, and then 29. Now if I graph it, it looks much neater. So be aware, the calculator won't tell you if you made a typo. You have to, most of the time, you've got to check for it. Okay, this looks like a quadratic to me. Stat, calc, quadreg. R very close to 1. This is going to be a tricky one to round. So let's go to the nearest hundredth again, see if that's enough. 3.01 x squared. Even to the nearest hundredth, the b value rounds to 0. So minus 7.9. Round the 7.89 up. So let's see if that works, or if we need more decimal points. 3.01 x. X squared minus 7.9. Yeah, that's plenty close enough. So there's our function. Now the next one, we're going to put in the data, we're going to leave off the hundredth, although you certainly could change the decimal point if you wanted. We will write the model by getting the equation of best fit. We will use the model to predict, and so this will be to predict for y, and this will be to predict for when the year is 2010. This will be to predict for when y reaches 85. Really important in this kind of problem. Years since 1950. If you do that and you go ahead and put in, so this is 0 years since 1950, 10 years and 20 years and 30 years and 40 years and 46 years, and then you forget you've done that and put in 2010, you're going to get a really strange answer. So again, be aware of that. If you get an answer that doesn't make any sense, go figure out why. I'm going to go in, I'm going to put in these values and generate a model and come back. So I've put in my data, and I've looked at my graph, and I've decided that the best fit here is actually a linear equation. You could try for cubic, but the values turn out to be, the coefficients turn out to be very, very small, small enough that it would be very difficult to put it in the calculator. So this, it's not a perfect fit. R squared is only about 0.98 rather than 0.999, but it's decent. So the equation I came up with is y equals 0.49x plus 57.68. To predict the percent of the population living in metropolitan areas in 2010 is 60 years since 1950. So what I did was I used this equation. You could go ahead and plug in 60 for x by hand, but you can also go to table set, set my start value at 60. Delta table can say 1. All right, so when x is 60, y is 87.08, or roughly 87.1%. To predict what year we'll have 85% of the population living in metropolitan areas, well, that's over 85%, so let's scroll back. Oops, sorry, gotta do it in the axis. Scroll back until we hit roughly 85%. That's roughly 56 years after 1950, or 2006.